Alright, in this video we'll be going through the 2018 electricity exam. The way I recommend you watch this video is to pause the video before every question, try the question yourself. Once you completed the question or get stuck, unpause the video to see how I go about getting the answer. Casey sets up a battery, a switch, and a 3 ohm light bulb in series. The battery voltage is measured to be 6.02 volts when the switch is open. However, when the switch is closed, Casey notices that the battery voltage drops to 5.85 volts. Explain why the battery voltage is less when the switch is closed. Alright, so this is obviously due to the fact that our power supply or our battery and our circuit wires have an internal resistance. And so therefore when current flows through our battery and our wires, some of that energy is lost to heat, okay? And so therefore each coulomb of charge carries less energy. And so therefore when current flows throughout the circuit, aka when the switch is closed, the voltage across the battery, which is our terminal voltage, is less than the EMF, which is the voltage of the battery and the switch is open. Alright, and so you can write that in. Casey measures the current through the circuit to be 1.89 amps. State the EMF and show that the internal resistance of the battery is approximately 0.09 ohms. So the EMF of the battery is equal to the voltage when the switch is open, okay? And so that is 6.02 volts, okay? 6.02 volts, alright? And so we can see that when the switch is closed, the terminal voltage of the battery is 5.85 volts, okay? So I got that value from here. And so therefore, we can say that the voltage drop due to our internal resistance, aka that is our lost volts, okay? So our lost volts is equal to our EMF minus our terminal voltage, which is equal to 6.02 minus 5.85, and that is equal to 0.17 volts, okay? And so therefore, as V is equal to IR, where our R this time is going to be little r because that is our internal resistance, and that is what we're trying to find. We're trying to find our internal resistance, so we can rearrange for our internal resistance. And we get the voltage across our internal resistor, which is 0.17, divided by the current throughout the circuit, which is given as 1.89. And that's equal to 0.0899, and obviously we can round that to 0.09 ohms. There we go. Casey now adds a capacitor in series with the battery and closes the switch. Casey measures the voltage across the capacitor as it charges. Using the information from the graph, determine the capacitance of the capacitor. Alright, so we know that our time constant is equal to RC, and so therefore we can find our capacitance from our time constant. We are already given the total resistance of the circuit as 3 ohms, okay, so that's going to be our R value, and all we need to do is find our time constant. The way we can do that is we can take our max voltage value, which is 6 volts, okay, or it's actually 6.02 volts, okay, to be precise, okay, and we can take 63% of that value, and then we can find that time value at that voltage value, and that will be our time constant. Alright, so we take 6.02 multiplied by 0.63, okay, and that's equal to 3.8 volts, okay, and so if we look at 3.8 volts, that is going to be right over here, and as we can see, that is equal to 1 times 10 to the negative 5 seconds, okay, so 1 times 10 to the negative 5 seconds, alright, so that is our time constant, and so therefore our total capacitance is equal to 1 times 10 to the negative 5 all over 3, and so our capacitance is equal to 3.33 times 10 to the negative 6 farads. There we go. Casey discharges the capacitor and removes the light bulb and begins to charge the capacitor again. Casey predicts that by removing the light bulb, less energy will be converted to light and heat, so the capacitor will charge more quickly and have more energy stored once fully charged. Use physical reasoning to discuss each aspect of Casey's prediction. You should discuss, with explanations, whether the capacitor will charge more quickly than before, whether less energy will be converted to light and heat during the charging process without the light bulb, and whether more energy will be stored in the fully charged capacitor. Alright, so as our time constant is equal to the resistance times the capacitance, when we remove the light bulb, we decrease our resistance, and so therefore our time constant is also going to decrease, meaning our capacitor will charge faster, okay? Also, as V is equal to IR, and our supply voltage has not changed, if we decrease our resistance, therefore our current must increase, okay? And so therefore, as current is increased, that means more current is flowing through our internal resistance, meaning we're going to lose more voltage due to our internal resistance, okay? Alright, and so therefore we're going to lose more energy to heat and our surroundings, okay? And so that means the same amount of energy will be lost to heat during this process, okay? Now, will more energy be stored in the capacitor? No, it won't, because EP is equal to half CV squared, okay? Our capacitance has not changed, and the voltage across our capacitor once it's fully charged also has not changed, okay? Because the voltage of our supply has not changed. And so therefore the energy stored in our capacitor also will not change, okay? And so you can write that down. KC is using an electromagnet that has an inductance of 4.5 times 10 to the negative 1 henries and a resistance of 2 ohms. KC connects it to a DC voltage of 12 volts with an internal resistance of 0.09 ohms. Determine the current through the electromagnet a few minutes after the switch is closed. Alright, so a few minutes after the switch is closed, we know that the electromagnet is going to act like an ideal wire, okay? And so there's going to be no back EMF, and so therefore the current through the electromagnet is going to be equal to the voltage divided by the total resistance. In this case, the total resistance is going to be equal to 2 ohms from here and 0.09 ohms from there. And so therefore our total resistance is equal to 2.09 ohms, okay? And so therefore V, which is 12 volts divided by 2.09, gives a current of 5.74 amps. There we go. KC opens the switch and a large spark jumps across the terminals of the open switch. Explain how the coil can produce such a high voltage when the switch is open. So when the switch is open, the current drops to 0 immediately, so there is a high rate of change of current, okay? So this value is extremely high, alright? Also, as our time constant is equal to the inductance all over the resistance, if the switch is open, this is then theoretically infinite resistance. When the circuit is broken, that gap theoretically has infinite resistance. So we have a large resistance, okay? So a very large resistance, and so that means our time constant is going to be very, very small. Okay, and so therefore, as our EMF produced by our inductor is equal to negative L, change in current all over change in time, if our time constant is very, very small, that means the EMF produced by the inductor is going to be very, very large. Therefore, as the potential difference is so great between the two terminals, a spark is produced to jump that gap. Alright, and obviously we are not limited by Kirchhoff's voltage law because we are not in a closed loop. Alright, because the loop is open. And so you can write that in. To prevent damaging sparks, KC places a 20 ohm resistor in parallel with the electromagnet. At one point shortly after the switch is closed, the rising current drawn from the battery has reached 2 amps and the back EMF of 9 volts has been induced across the inductor. Show that the current through the electromagnet at this time is 1.41 amps. Alright, so we have a back EMF for our inductor, like so, and that is 9 volts, okay? And so therefore, if we go this way for our Kirchhoff's voltage law, we can see we have a 12 volt rise, okay? And so we get 12 volts. And we minus the voltage drop due to our internal resistance. And so this voltage drop is going to be equal to the current, which is 2 amps, multiplied by the resistance, which has 0.09 ohms of resistance, okay? And then we carry on through here, and we have another voltage drop over here. And this voltage drop is going to be equal to the current through the coil, multiplied by the resistance of that resistor, which is 2 ohms, okay? And we also minus the back EMF of our coil, which is 9 volts. And that is all equal to 0. And as we can see, we only have one unknown, and so we can just rearrange for that unknown. This value right here simplifies to 0.18, so 12 minus 0.18 minus 9 minus 2 times the current through the coil is equal to 0, okay? And so 12 minus 0.18 minus 9 is equal to 2.82 minus 2 times the current through the coil, and that's all equal to 0. And so therefore 2.28 is equal to 2 times the current through the coil. And so therefore 2.82 divided by 2 is equal to the current through the coil, and that is equal to 1.41 amps. And as you can see, that is the value that we're trying to find. After many more minutes, the current through the coil is at a steady 5.72 amps. The switch is now opened. Plot the graph of current versus time for the electromagnet as the current falls to 0. Explain how the presence of the 20 ohm resistor protects against high voltage sparks that KC witnessed earlier. Alright, so let's just look at that situation. We can see that when the switch is opened, obviously this part of the circuit is now disconnected. Okay, so now we have a series circuit like so. Okay, and so now the EMF of our inductor can act as a supply voltage, and so therefore current can safely flow through until this EMF dies down. Okay, and so therefore that prevents sparks from trying to jump the gap. Alright, you could also say that this 20 ohm resistor provides a low resistance pathway. Okay, it's low resistance in comparison to this. Okay, so remember that this gap right here is theoretically infinite resistance, and so this 20 ohm is much, much smaller. It's a much, much lower resistance pathway. Okay, and so therefore, because our time constant is equal to the inductance all over the resistance, because this is a lower resistance pathway, meaning that this value is smaller, therefore we have a much higher time constant, and so therefore as our back EMF is equal to negative L change in current all over change in time, if our time constant is greater, therefore our back EMF is smaller, and so we have a smaller current. And so not only does the 20 ohm resistor provide a pathway for the charge to flow in a series circuit, the EMF that is produced by our inductor is also a smaller value, okay? And so that is part 2 explained. Now we need to do part 1, so plot the graph, all right? Again, we know our time constant is equal to L all over R. Our inductance is given right here as 4.5 times 10 to the negative 1, and so that's equal to 0.45, like so, all over our resistance, which when the switch is opened is equal to 22 ohms, because we have 20 ohms right here and 2 ohms right here. Okay, and so that's 22 ohms. Don't need the units for that. And so that gives a time constant of 0.02 seconds. All right, and so therefore this is going to be 1 time constant, 2 time constant, 3 time constant, 4 time constant, 5 time constant. All right, and obviously 6. So we start at our max current, which is 5.72. Okay, so 5.72 is roughly going to be over here. Okay, and so after 1 time constant, 5.72 multiplied by 0.37 is equal to 2.11 amps. All right, and so 2.11 is roughly over here. Okay, and then we can find it after 2 time constants, which is equal to the max current times 0.37 squared, and that's equal to 0.78. Okay, so 0.78 is roughly over here. Okay, after another time constant, we put this to a power of 3 now, and that's equal to 0.3 amps. All right, and so 0.3 amps is roughly over here. Okay, and so we can do one more times 0.37 times 10 to the 4, and that's equal to 0.1. Okay, and so now we are basically reaching 0, and so now we can just draw our exponential decay like so. Okay, there we go. Casey is experimenting with building inductors and capacitors. To make a capacitor, Casey places a thin layer of rubber between two 1.2 meter squared aluminium plates and then squeezes the sheets together. The rubber has a dielectric constant of 8.9 and is compressed to a thickness of 1 times 10 to the negative 4 meters. Show that the capacitance of Casey's capacitor is 9.45 times 10 to the negative 7 farads. Alright, so we know the equation for our capacitance is equal to our permittivity of free space times our dielectric constant times our area of overlap between the two plates, okay? So I can draw that better. Area of overlap between the two plates divided by our distance. And so we can simply plug in our numbers. E0 is given in our formula sheet, and that's 8.85 times 10 to the negative 12, multiplied by our dielectric constant, which is given up here, of 8.9, multiplied by our area, which is 1.2, all over the distance between the two plates, which is given right over here, as 1 times 10 to the negative 4. And as we can see, this gives a capacitance of 9.45 times 10 to the negative 7 farads. And as we can see, that is the value that we're trying to find. To make an inductor, Casey winds several hundred turns of insulated copper wire around an iron rod. Casey wants to test its inductance. Casey connects the circuit shown below. The voltage across the lamp is measured to be 4.6 volts RMS, and across the inductor to be 11.1 RMS. Show that the inductance of Casey's inductor is 3.81 times 10 to the negative 2 henries. Alright, so as this is an AC circuit, we know that the current throughout all points throughout the circuit is going to be the same at any given time. And so therefore, to find the current throughout the circuit, we can find the current through this lamp, okay? Because we're given the voltage across the lamp and the resistance of that lamp. And so the IRMS is equal to the VRMS of the lamp, which is given as 4.64 divided by its resistance, which is equal to 5, and this gives a value of 0.928 amps. Alright, and so therefore, if we apply Ohm's law to our inductor, we get V is equal to I multiplied by the reactance of the inductor. And so therefore, the reactance of the inductor is equal to the voltage across our inductor divided by the current, which we just found, okay? And now the voltage across the inductor is 11.1 divided by the current, which is 0.928. And so this gives a reactance of 11.96 ohms. Now from here, we know that the reactance of our inductor is equal to omega L. And so therefore, from here, we can find our inductance because we're given the frequency of our power supply, and we know that omega is equal to 2 pi f, okay? And so therefore, our omega is equal to 2 pi times 50, which is equal to 100 pi. Okay, and so our inductance is equal to the reactance of our inductor divided by 100 pi. Okay, and the reactance of our inductor is equal to 11.96, and so this gives an inductance of 0.03807 henries. Okay, and this rounds to 3.81 times 10 to the negative 2 henries. And as you can see, this is the value that we're trying to find. Casey adds in the 9.45 times 10 to the negative 7 farad capacitor to create an LCR circuit. The light bulb barely glows. Casey switches the AC power supply to its maximum frequency setting of 400 Hz. Determine the new impedance of the circuit. Alright, so from here, we know that our XL is equal to omega F. Okay, so now our omega is equal to 2 pi F. And so now we have a new frequency of 400 Hz, so that's 2 pi times 400, and so that's equal to 800 pi. So that's our omega. That is not F, that should be L. There we go. And so our reactance of our inductor is equal to 800 pi multiplied by the inductance of the inductor, which is equal to 3.81 times 10 to the negative 2. All right, we found that in the previous question. And so the reactance of the inductor is equal to 95.76 ohms. Alright, so now that we have the reactance of the inductor, we can find the reactance of our capacitor, and we know that's equal to 1 all over omega C. Obviously, we just found our omega, and that's 800 pi, multiplied by the capacitance of the capacitor, and that's given right over here. So that's 9.45 times 10 to the negative 7. Alright, and this gives a reactance of our capacitor as 421.04 ohms. Alright? So as we can see, the reactance of our capacitor is much larger than the reactance of our inductor, okay? So if we're making our phase diagram, we obviously know that we're going to have the value of our resistor coming to the right, like so, okay? And the value of our resistor is 5 ohms, okay? So this is our R value, okay? The value of our capacitor is way bigger, okay? So this is the reactance of our capacitor, and that's equal to 421.04 ohms. Okay, and the reactance of our inductor is slightly bigger than the resistance value, and that's 95.76 ohms. Okay, so that's the reactance of our inductor. And so our net reactance value is probably going to be roughly like so. Okay, so this is our X net, and our X net, remember, is when we take our inductance value and we minus it from our capacitance value. Okay. And so in this case, that's going to be 95.76 minus 421.04, and this gives a value of negative 325.82. Now remember, the negative in this case is just saying that it's pointing downwards, okay? So we don't really need that for this calculation because we already see that it's pointing downwards. So it's 325.82, and so we can write that in if we want, 325.828, sorry, not 82. There we go. And so therefore our total impedance is going to be like so, okay? Where we make a phasor diagram, okay? So this is our R value, and this is our X net value, and this is our total impedance, which is the resultant vector. And so therefore our Z is going to be square root our X net, which is 325.28 squared plus 5 squared, and this gives a value of 325.32 ohms. Calculate the resonant frequency for the circuit and compare it with the maximum frequency setting of the power supply. Alright, so when the circuit is in resonance, this is when XL is equal to XC. We know our XL is equal to omega L, and our XC is equal to 1 all over omega C. And so therefore, omega squared LC is equal to 1. Omega squared is equal to 4 pi squared F squared. Okay, and so therefore 4 pi squared F squared LC is equal to 1, and so therefore F is equal to 1 all over 2 pi square root LC. Okay, we know our inductance and we know our capacitance from previous parts of this question, and so we can simply plug in our numbers. We get 1 all over 2 pi multiplied by square root 3.81 times 10 to the negative 2 multiplied by 9.45 times 10 to the negative 7, and this is all equal to 839 Hertz. Alright, and so as you can see, this is much higher than the maximum frequency of the circuit of 400 Hertz. Okay? Describe how Casey could physically alter the inductor and capacitor to increase the current through the light bulb using this power supply. Alright, so right now we have a case where our reactance of our capacitor is much greater than the reactance of our inductor. And remember, if we want to maximize the current in an AC circuit, we want our total impedance to be at a minimum value, and our total impedance is a minimum value when our circuit is at resonance. That is when our XC is equal to our XL, okay? And so what we need to do is we need to make the reactance of our capacitor smaller and the reactance of our inductor higher, okay? And so our reactance of our capacitor is equal to 1 all over omega C, meaning is inversely proportional to its capacitance, and the reactance of our inductor is equal to omega L, so the reactance of our inductor is directly proportional to its inductance. And so what we need to do is we need to both increase our capacitance and increase our inductance, okay? If we increase our inductance, we increase our reactance of our inductor, and if we increase our capacitance, we decrease the reactance of our capacitor, which is what we want to do, okay? So ways to increase our capacitance. If we look at our capacitance equation, like so, we could make this D value smaller, aka bring the plates closer together, and that would also increase our capacitance, okay? So we could make the plates closer together. We could increase the area by increasing the overlap or by using larger plates, okay? So if we increase our area, our capacitance will increase, alright? And we could also use a material with a higher dielectric constant, okay? So a higher dielectric constant will increase our capacitance. As for increasing our inductance, we could add more coils to the inductor, alright? And we could also increase the area of our coil, which will increase our flux, right? Because we know our flux is related to the area. And so you can write those in. And with that, we're done. See ya.